Yes. Well, it looks like we can begin.
How you doing?
Crap. Hi, how are you?
Great.
Thanks.
You bet.
Welcome back, everyone. This is huge. It's our anniversary. My husband likes to embarrass me every semester. We're going on 4 years. I said 5, but that's kind of embarrassing as a math professor. I forgot how many years we were married. Thanks. Well, getting back on track. Welcome back, everyone. We are now in section 1.4, and it'll take me just a couple minutes to unfrazzle myself, but any questions at the moment to start out? How about folks in Zoom? Any questions so far? Okay, well, we're in section 1.4, the matrix equation. And I'm going to try to post my notes a little bit early since, I mean, if we finish a set of notes 20 minutes early, we'd like to walk into the next section, but more just so that you can have them available, print them ahead or download them before class, kind of know what direction we're going before we even get to that section there. So occasionally you'll see extra sections posted. If I get really behind, then you might not see it. It'll be your indication I'm having a pretty busy week sometimes. But for the moment, it's worth remembering or reminding ourselves that our first assignment's due. So this is assignment 1 and assignment 2, those 2 sets. And that's going to be kind of atypical for this section. 1.1 was pretty short and 1.2 also was pretty short. But typically we're only going to have one section that's going to be coming due per day, not multiple sections. That's kind of dicey to organize all that stuff. Any questions at all, folks, about turning in the assignments or any of the problems on those assignments? Okay, and as far as the grading is going to go, if you turn in a hard copy in class today, then you'll get a hard copy back when you're next in class. I'm going to try to get these graded within the week, but I think most of my grading is going to happen on the weekend. If you'd like to get your assignment handed back to you digitally, then you can just email it directly to my email address. The same address right up here on the syllabus. Let me just proofread it. Yeah, that looks like the right one. So if you're working on your homework digitally, maybe you're coming in through Zoom, Pocatello campus, or otherwise, then just send it directly to that email. I'll mark it up and send you back a PDF copy. Any other questions or comments, folks, about the homework assignments, turning them in or anything along those lines? Okay, now going down to section 1.4, we're starting to work through our list of definitions that we need to get through in linear algebra. And what 1.4 is going to do for us is, let's take a quick peek at 1.3. The matrix equation AX equals B gets us to linear independence. What we're going to be looking at is a matrix equation. Then we're going to, in section 1.5, look at a specific equation where A times X equals the 0 vector. We are extremely interested in the solution sets of a homogeneous system of that kind, because once we know we have no non-trivial solutions, we have linear independence. So that gets us to one huge part of linear algebra in this chart here. So that's the direction we're going in. And here's how we'll start. So example 1 is kind of just a warm-up kind of example. We need to get used to our notation, and we've talked about rows and columns a lot, but now it's a really big deal out of nowhere to know exactly what we mean when you say row versus column. One thing you can do as a notational device is anytime you see, say, a column vector or a row vector or an outright matrix, describe the rows in this way. This particular vector as a column vector has 4 rows, and well, it's just 1 column, so we think of this as a 4 by 1. So we want to know the number of rows, number of columns, and we can say for this one, let's say get my colors going. There are 4 rows, 1 column, and the next comment we can say is that U is in R4, having those 4 different entries or 4 rows for that particular vector. So this will be all very common notation. And this notation, I'm writing it in orange, meaning you don't have to write that down in your work. But sometimes when we do matrix times a vector or a matrix times a matrix, that little thing in orange is going to tell you just about everything you want to know. Like, for example, Can you multiply your matrix times a vector? Is it even defined? And if it is defined, if you can multiply it, these kinds of things will tell you, well, what is the size of the output result? How big is the product in terms of rows and columns? So that's our first one down, just an ordinary column vector. And if we look at this one, any volunteers in the class using the same notational device here, would you call this a 3x4 or a 4x3 or otherwise? Good call. This has 4 rows going this way and 3 columns going this way. So this will be a 4x3 object. So finally, we can say, just to finish off the instructions to the letter, this has 4 rows going this way. Going this way, these are the columns, so 3 columns. And then we can say overall that this matrix A is in, we start by saying R because the entries we're putting in that matrix are just real numbers for this particular course. Other courses would use this potentially complex numbers for your matrix or your vector, but we're going to stick with real numbers as an introductory course. And we'll say, well, A is not in the set of real numbers because there's 4 rows, so we'll go 4 by 3. We mentioned last class, that's a vector space. We'll later describe that as a 4-dimensional vector space. But this is also a vector space. It consists of every single matrix of size 4 by 3 with any real numbers you'd like put in that array. So that's just as honest as a vector space as this one was. And we'll be studying both of them. We'll study this one in a lot more detail in chapter 2 when we do matrix times matrix. That's kind of our warm-up, just getting started with linear algebra and the notation. Any questions or comments, folks, about what we wrote here? Okay, so definitely getting rows and columns mixed up, it's easy to do, but in linear algebra, it's almost unfair. That causes a lot of problems. So this is always a good document to return to, just as a refresher. Finally, here's our definition. What our definition is getting into is, well, linear combinations, and so it's also tied in with spanning. It says, if you have an n by n matrix, let's circle some portions of this. That n there turns out to be really important. We'll denote the columns just as a A1 through AN. So here they are. That's an entire column vector. It has m entries, so m entries going this way. And it looks like we have n different columns. Then we're going to multiply x by x, but that's a vector coming from Rn. That n was also important. If there's a mismatch from here to here, the whole product is undefined. You have to have the same number of entries in your vector as there are columns in the matrix. Well, the reason for that is the definition says to pair off your entries with the corresponding columns of the matrix A. So here's how they paired off. And you're forming a linear combination. We'll take the first entry times the first column, second entry times the second column. There it is. And so on until you get to the last entry times the last column. So definitely you have to match up number of columns with number of entries, or else this does not make any sense at all. So that's our definition. And what's nice about it is this is a familiar object. We've calculated linear combinations before. We went a step further and looked at the span, which is the set of every potential linear combination. But what we'll be doing now is not necessarily writing this out every single time. This definition is great for learning, but sometimes it's great for just conceptualizing what is a matrix times a vector going to result in. But it takes too long to do it this way every single time. That's why I put this in the homework. Not a bad idea if you want to do both ways of multiplying, the definition here or the row vector rule that we're going to describe. But we'll try it twice on this one and do it just the one way, the way it's typically calculated once you're getting good practice on this concept. Well, let's take a look. For this matrix A, first thing I'd want to do is describe how big it is. This is a nice square matrix, 3 by 3. Next thing you can look at is the vector multiplying came from R3, and that's good. It means it has 3 rows, 1 column, meaning it's a size 3 by 1. The moment we specify that information, we look here and look here. There's a mismatch. You will say undefined, and you don't have to do anything further. even if the instructions say explain why the product is undefined, you showed me this work here, and maybe there's a 3 and a 5 there. You could just say undefined, and to me, that's a decent explanation. You showed me why it's undefined, and that's pretty much all I'm looking for. But this one is defined, so here's how we'll calculate it out. We're going to take the entries in the vector x, here's those entries, and multiply them by the corresponding columns of the matrix A. So it starts off by doing -4, multiply first column, so 1, -3, 1. Then next entry plus, well, this one's not exciting, but if you want to show the linear combination verbatim, there it is. That's that scalar 1. It's not going to change much, but we've got it. We're going to multiply this next entry, so following that same process. Excuse me, this next vector, which is -3, -4, 6. Then rinse and repeat. Plus this last entry right here, 2, multiplying the last column vector, that one, 0, 2, 1. And this is the reason why, well, it's the correct definition, but this is the reason why it looks kind of clunky. It's a lot of work to calculate the whole thing by this process. But the good news is it always works, and we're just about to get through it. We just now have to crank out what does this linear combination result in. Any questions first with this first critical step, just writing it out? Okay, if we're happy with that, it's now just down to crank out all these operations. I'll start with the scaling. So first vector is going to result in -4, +12, -4. This one is nicely easy to scale. We'll just say plus, same vector, -3, -4, 6. One is still the multiplicative identity, even if it's multiplying an entire vector. And this one gives us a result of 0, 4, 2, after scaling all entries by 2. Last thing to do is do the vector additions. So we'll go across corresponding entries in the rows. For row 1, looks like a -7. Row 2 will give us a +12. And row 3 is altogether a 4. We did it, folks. That's our very first matrix times a vector product. We'll later on do a matrix times a matrix in chapter 2, and it uses these kind of rules. But we need to get faster at these kinds of rules, or a 3x3 matrix times another 3x3 matrix. We wrote out all these steps. That's like a couple pages of work all of a sudden. So we do need some shortcuts. So this will be, although this is part A. Oh, this is version 1. This is by the definition. Now let's do version 2. And just again, another reminder, you don't have to do it twice in your homework. You can pick one or the other, and that is acceptable. But in version 2, let's start by writing in just the original matrix. 1, -3, 1, -3, -4, 6, 0, 2, 1. It's multiplying -4, 1, 2. And I'll use yellow highlighting to show how this is going to work out. One thing you can note, though, is we know that this is defined, but the size of the product can be found this way. It's those outer dimensions that says your result is 3 by 1. The inner size just tells you whether you can actually crank it out or not. So looking before we leap, we know we're going to result in a 3 by 1. It seems like a small step, but that helps a lot because if you know what goes here, and if something is undefined, you'll realize immediately things are just not fitting. Okay, so the reminder on how this goes is, if you ever calculated a dot product or an inner product, that's essentially the idea with this. If you haven't calculated those kind of products, no worries. We're going to describe it right here. So using yellow to show where we're working at, we're trying to come up with this very first entry. That means we're involving the very first row going this way, and we'll always use that entire column. Next thing you'll do is visualize, maybe turn your head if you need to. This entire row overlaps with this one, and we just multiply corresponding entries. So it's going to be 1 times this -4. Oh, hang on, let me do that a little bit slower. It'll be that 1 times the -4 Let's write out here just as scratch. It'll be this -3 times this +1, and then 0 multiplying that 2. So we'll get a -7 altogether. But typically we don't write out this, we just kind of do a mental tally as we go. I'll write it out here just for the scratch work to tie it together. Once we're done with that entry, we move down to the second entry here, and we use this row to form the inner product. We'll just take the corresponding entries. This is entry 1, 2, 3. Multiplying these corresponding entries, you can imagine them moving over and rotating, becoming vertical if you'd like. So multiplying them through, this will be +12. Let me recall we're using a pen for that, +12. Then in this entry times this entry will give us a -4. This entry by this one will give us +4. So that one will result in a 12 as well, and we just throw in a 12 there. Does that make sense to folks, how this visualizes? Awesome. And that's another thing that's weird about linear algebra. We're only in section 1.4, and you might have noticed we do loads and loads of really fast arithmetic operations like this. So that's a side benefit of linear algebra. You get pretty good at these kinds of multiplications, additions, subtractions. But now let's move to last entry here, which means we're involving the final row here. Still multiplies the same column. Let's run this through. It's 1 times -4, so -4 to start. 6 times 1, so +6. And then 1 times 2, so +2. This is going to give us a 4 altogether. And so we throw a 4 there in our final entry for the product. That means we've got it, folks. That's a matrix times a vector. And if it's a matrix times a whole other matrix, it's still the same kind of idea. We just build on it a little bit more. Any questions, folks, on either way of doing it? Okay, and it is a really good reminder, however. I would say a good goal for this section, really for chapter 1, is this method here. Let's say this method is highly important. Only because we'll multiply so much that if we do the linear combinations each time, like we said, it turns out that takes way too much effort to just do a matrix times a matrix even. So that was our first example. And let's now go to the next. Same instructions, we're just going to try to multiply this out, but let's focus on this one. We'll shun the linear combination definition because this is the one we truly want to practice. So we have, to start off, a matrix. It's of size, well, 3 rows, 2 columns, so it's of size 3 by 2. So we go over here, the column vector is of size 3 by 1. So we have to make a judgment now. Is this defined or undefined? I agree, this is not looking so good. How do folks feel in Zoom? Would you say this is a good or bad situation to be in? I agree with Pren. This is looking really quite terrible. And this is pretty much what it comes down to. If a product is undefined, then explain why. Imagine this is, say, an exam 1 problem. Pretty much all I would write down is this and this. Well, the whole 3 by 2, the whole 3 by 1. But here we can say undefined. I would accept that for full credit. But if you want to give a little bit more detail, maybe you're answering in a homework set. Homework sets are really good for studying on exams. You might give a further description. You could say, let's put this in parentheses to emphasize you don't have to say it. The number of columns in the matrix does not equal the number of rows in the vector. So the product is undefined. My hand is getting tired at this point. It is a lot of writing, but sometimes that is worth it. It's a kind of a judgment call. exam setting, it's good to be terse. In a homework setting, this doesn't hurt either, but it's not required. If you have this thought in the back of your mind, then that's the most important thing. Well, any questions, folks, on that quick one there? Okay, defines are great. You just move through them really fast once you spot them. Next one doesn't look very well. I mean, that's a strange matrix, and that's, well, nothing too strange about the vector. When we look at it really closely, well, let's see if it is defined or not. We can describe the size of that matrix as being 2 by 4. Then when we look at the vector, that vector comes from R4. It has 4 entries. It's of size 4 by 1. So we know this is defined. There's a match here and here. We'll get a product for this. It's also a good idea to show the size of the product, and you can do that from here and here. The result of A times X in this setting is going to be a 2 by 1 column vector. So we'll come over here and just write out a really short column vector like that. Okay, so our goal is to do this method. We're going to just take a row times the vector here and throw in the entry. We don't necessarily want to do this as much because the idea is not to write too much so we can move the product quickly. So let me show you about how I would probably do it. Here's the entry I'm trying to calculate. It means we're using row 1. And going down the line, I'm going to pair up these 4 entries in the row with the 4 entries in the column, multiply and tally them together. So we'll start with 6 plus 0 minus 3, so we're at 3, minus 18, so we're at negative 15. That look right to folks for a negative 15 on that one? Awesome. If you're happy with that, it's just rinse and repeat. So for this entry here, we need to use the last row. Makes sense. Last row will give us a last entry and pair them up in this way. 3 times 6 for 18. Then minus 4 takes us to 14. Minus 2 will take us to 12. Then minus 3 takes us to 9. And we've got it, folks. That's the whole result of that matrix times the vector. We get something in R2 this time. Kind of strange. This is something in R2 by 4. This is a vector in R4, but somehow we end up in a totally unrelated seeming space. We end up in R2 with this product. Well, any questions at all with the rundown on matrix times a vector situation? Okay, now that we have that, we have more interesting ways we can describe our systems of equations. Let's get this to the next page, maybe. So this problem right here is just a way to now look at different notations. If we can describe multiplying a matrix with a vector, then we can take our system of equations and just describe them as a matrix equation. When we say matrix equation, we mean this right here. I know that doesn't seem like very worthwhile highlighting, but a lot of times my comments come from grading exams in particular. And one thing that's kind of easy to miss in an exam setting is when we're being asked to show a matrix equation, it's got to be this. So here's the comment. This is not an augmented matrix. Well, the augmented matrix is not what we're using when we say a matrix equation. That's just the structure that we put down if we're going to solve the system of equations itself. So that's easy to kind of conflate. It's good to keep separate. That's also kind of the purpose of this problem right here. We have a matrix equation. So here's the matrix A coming from AX equals B. This right here is X. X itself describes X1, X2, X3. So we'll often just write out X itself instead of all of the entries. And well, we have equals here. So here's A times X equals, and that's the vector B, the right-hand sides of all the linear equations. But if we want a vector equation, this is pretty much all we've got to do. We're not going to multiply using this method. If we want to write out the matrix equation, we're multiplying with this method. We're just going to write out the linear combination, essentially. So imagine this is pretty much your matrix equation right here, well, the left-hand side, except it goes x1, x2, x3. So writing that all out, multiply x1 into column 1, and we get x1 times 1, 1, negative 3. So that's our first part of the linear combination. There must be a plus right here to form a proper linear combination. Let me just move over to the second entry, x2, multiply the second column, 3, 5, negative 7. Likewise, go x3, multiply by third column, which is negative 4, 2, 6. And last right-hand side is negative 2, 4, 12. So that's our vector equation. Any questions at all, folks, on forming that equation down there? Okay, next thing it asks, really just kind of for a review, write the system of linear equations, but don't solve the system. This could be a potential exam problem where it's just a short concept question about expressing your system of equations in different formats. You'll see the matrix equation, the vector equation, and a system of equations. But getting the system of equations is pretty much a matter of really just doing this. I probably wouldn't even look at the vector equation, to be honest, although it does help if you decided to. It's just as simple to look at the matrix equation. All these coefficients, 1, 3, negative 4, correspond to x1, x2, x3, and negative 2 is the right-hand side to the first equation. I think that's honestly easier to read out the matrix equation than the vector equation if you're just going to write down the full system. So I'd go this way, focusing on row 1. Here's equation 1. 1 times x1, I'll just call it x1, plus 3x2, minus 4 times x3, equals negative 2. Then go down to row 2, do the same thing. x1 plus 5x2 plus 2x2 equals 4. And last one, negative 3 times x1 minus 7 times x2 plus 6 times x3 equals 12. Now we've got it, folks. That's our system of equations. Sometimes you see this in the lecture notes, and I pretty much put it in the lecture notes just so that we're familiar with it on an exam. Sometimes on exams, it's all about the concept, but don't waste any extra time trying to solve it. Yeah, go ahead. 2x3 on this entry right here, or oh, this one right here. That isn't picky. Thanks for spotting that. Without a correction here, that combines as like terms, and we're looking at 7x2. Good eye. Thanks for spotting that. This one should be a 3, absolutely. For the notes, that's definitely not a nitpick. That's absolutely correct. But if this was a real exam problem, I don't think I would take off points for that kind of error, because you're demonstrating the understanding going from here to here. Subscript error, I'd probably circle it, but that's about it. But thanks for spotting that for the notes. Other questions or comments at the moment? Okay, well, we've got lots of ways to write out our equations, whether it's a system of equations that you throw into an augmented matrix, or a vector equation, or a matrix equation, the solution set is exactly the same. So they're all just different ways to look at the same kinds of objects. Well, let's now take a look at our next concepts. I left a little bit of a gap here intentionally, because this theorem is a humongous one. Let's put here just another big reminder. This is an extremely important alternative to the invertible. Let me spell that right to start off. Invertible matrix theorem. The invertible matrix theorem is punishing in some ways, but it tells you a vast amount of information all in one statement. The way it's punishing is invertible matrix theorem requires that the number of rows that'd be M, is also equal to the number of columns, that would be N. So it's a statement about square matrices specifically, size 2 by 2, 3 by 3, and so on. The vertical matrix theorem is one of those big theorems that's absolutely going to go on the back of an exam. It's not a theorem you try to memorize in full, but this one is probably going to make it to the back of exam 1 as well. It's an extremely important alternative because n by m is not square, and it's your next best thing if you want something like an invertible matrix theorem. Both theorems have this statement. The following statements, A, B, C, and D, are logically equivalent. Essentially, what that means is they're all going to succeed simultaneously, or they're all going to fail simultaneously. Say it a different way. If one statement's true, pick any random statement, say that one. If you can show that's a true statement, you have automatically showed everything else is true. That's pretty powerful because those are really big statements spanning linear combination solution sets. From a different point of view, if you find one statement here that's false, just one, say, for example, you found a vector B for which AX equals B is inconsistent, it doesn't have a solution, then you will know automatically everything else is false. There will not be a pivot in every row. Columns does not span, and not every vector can be a linear combination. So these statements, when they're logically equivalent, is really powerful. In fact, we've seen these kinds of things before whenever you use if and only if. That's when the logic goes one way to the left and one way to the right. This is like a big expansion of if and only if, in a certain sense. One way you can think about it is statement number A in this theorem is a statement about consistency. Whether the system is consistent or not. Statement B, it says it there. This is not a really big shorthand. It's a statement about linear combinations, obviously. I'll just write lin for linear, COMB for combinations. This is clearly a statement about spanning. And this last one is a statement about pivots. So theorem 4 becomes a huge cornerstone theorem in the entire book because it relates consistency, linear combination, spanning, and the pivot positions of your matrix into one compact statement, well, as compact as we can make it. And with a theorem like this, you need one good statement to actually access the theorem. Some parts of this theorem are actually kind of hard to show. For example, it might not actually be easy to show this very precisely and generically that any vector B is going to be a linear combination. That could be pretty hard. But this one is always easy. All you do is row reduce to echelon form, and you have found all the pivots in your matrix. That's like your gateway into theorem 4. It's easy to show that that's true, and it's easy to show it's false. You just use row reduction. And so if people are using theorem 4, they often go through it in that statement there. Show that's true. You've shown everything up here is true. Show that statement's false, and everything above is false. Let's put one big comment here to say the pivots, or let's say it's slightly different. Because of the pivots there, we use just echelon form to show this is true or false. So once you know the pivots, you're pretty much all set. Let's give that a try for example 4. But first, any questions or comments about the statements in this theorem? Okay, well, let's give it a try. It says, let A equal this. From here to here, let me try to highlight that a little bit better. That's really kind of hard. From here to here, we're just initializing the notation of how we're specifying A. We're referring to the columns A1, A2, A3. So A1 is this column right here. That's A2 and so on. The question being asked is B in a span of A1, A2, A3 for every B in R3? That's a really pretty compact question right there. It's abstract in a certain sense. It's asking if you pick any vector with 3 entries, can we form a linear combination that results in that vector by just scaling these, rescaling them, and adding them together? Who knows? That's a tough question, but it's a question about this right here. We're being asked to say or show if that's a true statement or a false statement. The easiest way to do it is we're going to analyze the pivots of the matrix and just make a conclusion based upon what we see. If there's a pivot in every row, we'll say yes to this question. If not, we'll say no. So here's how it starts. We're back to the land of row reduction. For this matrix A, nothing's been augmented here. So we're not too worried about this consistency and uniqueness theorem. In other words, we're not as worried about, what's it in these notes? Sorry. Because this matrix has not been augmented, let's go to 1.2. This theorem right here is of no use to us. And that's important because it's easy to think of all of our matrices as being augmented because it's practically been the case so far. But when you know you're dealing with just the matrix, ignore this theorem. Nothing has been augmented to actually use it. So we'll focus just on this matrix A, starting with row reductions. So let's just do the row reduction. Actually, I'll just write out here so I know what I'm looking at. 1, 1, -3, 3, 5, -7, -4, 2, 6. I used equality to start because I'm just writing out A. Now here's where the row reduction will begin. And for this row reduction, now that we've gotten some practice with homework and stuff like that, you can start taking more and more shortcuts and it's not as big of an issue. Let me know how this looks in class. I'm going to skip the detailed operation right here and we'll just work it out. First thing I'm going to do is work off this pivot position. Let's copy 1, 3, -4. Now to eliminate the entry right below, multiply row 1 by -1 and add to the row below. We'll get -1 plus 1, so 0. -3 plus 5, so a 2. Negative times -4 for a positive 4, giving us a 6. That's where I personally make mistakes, the double negation. Next, to eliminate the -3, we're going to triple row 1, add it to the third row. So that's going to be 3 plus -3 for a 0. 3 by 3 for 9, -7 for a positive 2. 3 by -4 gets us to -12 plus 6 gets us -6. So that's our new setup to that stage. Does that feel all right, folks, doing it this way for the row reduction? Okay. If you like, I can get back into the habit of specifying how the operation went, but I think this is also a pretty good goal for us as well. Become practiced enough with row reduction that you don't have to describe it each time, you just run through it. If you did multiple operations in this one step, that would be okay as well. So let's now do another operation. We have a pivot here. Next pivot is down 1, right 1 in this location. We only need echelon forms, so we don't need to force that to be a 1. It's better as a 2 to eliminate the 2 right down below with less work. So our goal is now eliminate the pivot under that second pivot position, copying in rows 1 and 2 to start. Gives us 1, 3, -4, 0, 2, 6. And now one thing I usually do is put a 0 here because the entry over here cannot possibly change due to the 0 above. I'm only changing the entries to the right of the above pivot. So multiply row 2 by -1, add to the row below. We'll get 0 here, -6 minus 6 for a -12 here. So now we have a pivot in this spot, and this spot, which means we're looking at a pivot in every row. So here's what we can do to tie together the whole statement. You don't have to specifically cite the theorem. You can if you'd like, that'd be possibly helpful for the notes. But if you do cite your theorem in your work, just to help looking back on it, you'd want to say theorem 4 of chapter 1. Our author does not have a great theorem naming scheme. So it doesn't, if you say theorem 4, there's loads of theorem 4s that could get kind of confusing. What I would do for the actual showing conclusions on this is pretty much say this. There is a pivot in every row. Rows are going this way, and we have found a pivot in row 1, row 2, row 3. Now, we just showed that's true. This is a very common theorem to use in linear algebra. So if you say this statement, I'm assuming you're using theorem 4 already. But we have to give the right conclusion. We're not going to write out all this stuff. We need to give the statement that actually targets the question. The question was, is B in the span of the columns of the matrix A, span of A1, A2, A3, for every B in R3? That's going to be this one right here. Is B a linear combination of the columns of A? So that's essentially our conclusion. And we can say, and so every B in R3 is a linear combination of the columns of A. We did it, folks. That's the conclusion of example 4. We know that no matter what you pick for this vector B, it could be 0, 1, 5, 1, 3, pi, anything at all, we'll reduce it, and you can find that that system is consistent. Doesn't matter what vector B you choose. We say sometimes the columns of A span R3. Let's say it this way. The columns of A spans R3. And if you can, you can say it in a even more compact way. You can say span A1 is the first column of A, A2 is the second column of A, A3 is the third column. So we just said the span of the columns of A with that statement is R3. So there's different ways you can say all this kind of stuff. But one thing you should say is, it's easy to miss this. It is not the span of A that is all of R3. It's the span of its columns specifically. Does that make sense to folks with those comments there? Okay, let's now take a look at another practice question just for more practice along these lines dealing with spans. This question here, example 5, it feels like the same sort of problem, but it's a little bit unusual. We have a specific vector right here. We're being asked, is U in the subset of R3 that is spanned by the columns of A? Why or why not? Now, this question is kind of dangerous in a certain sense. It's not asking if every U could be potentially spanned by the columns of A. It's asking about one specifically. That means this one's not a theorem 4 question. It's actually in the homework. That's why I brought to the notes today. Its purpose is just to tell the difference between the way the question's even being asked decides the method you have to use in linear algebra. There's a lot of really careful, precise reading, but we get good at it the more practice we put into it. So let's make a really fast comment here just to tie that together. Because we are interested in a specific vector being in the span of the columns of A, we will not use theorem 4. I mean, theorem 4 could work. If you use theorem 4 and it turns out there's a pivot in every row, then the vector was irrelevant, right? Every vector should be in the span. But if you row reduce this and there's not a pivot in every row, you can still be in the span of those columns. And so that's why theorem 5, it might work and it could be pretty fast, but in general, it's just not the best strategy to use. Best strategy is to do this. For this problem, we will row reduce the augmented matrix. So now we're back into augmenting something, the consistency uniqueness theorem. This one is back on the table for us. And the matrix we're going to augment goes like this. It'll be A augmented with U, with those matrix A and U specified there. Well, it's really just a review question as well. Yeah, go ahead.
So we can only use theorem 4 if it's not an augment, right?
I would say the bigger thing is that theorem 4 is more about this right here. If the question is about every single vector B, not a specific one like 4, -1, 4, then you definitely want to use theorem 4 in that case. And yeah, this is a good way to think of it too. Well, let me think of that again. Yes, with theorem 4, you wouldn't be augmenting. That is true. If you're doing this problem, you would definitely augment in this case. Does that make sense with those questions there? Awesome. Thanks for asking about those. Other questions at the moment? Okay. It's definitely kind of weird. This one's a throwback question from, I believe we did this in section 1.3. Whereas, let's actually highlight this portion. Only because they said for every B, and there's no vector B specified, we had to do the theorem 4 process, working out this way. So let's do a quick review problem, and we'll be back down to theorem 4 again for some additional examples. Any other further questions or comments? Okay, well, let's take a look. It says, let U be this vector coming out of R3. A is a 3x3 matrix. And the question is U in the subset of R3 that is spanned by the columns of A, why or why not? If it's helpful, you can rephrase a lot of these questions. You could use this notational device. It's not the best notational device, but the author uses it, so we'll use it too. Sometimes our author goes like this, A1, A2, A3. He's now specified that the columns of A are those three, and they're initialized in this way. So the whole question can now be rephrased. Is U in span A1, A2, A3? Sometimes it's a good idea to rephrase these questions. If you can make the question a little bit simpler, bring in some notation, rephrase it in your own terms, you're thinking about the overall problem, and that is a fantastic way to absorb linear algebra. Rephrase the question in a different way that makes more sense to you, or just looks familiar. So here's our vector U. Here's our column matrices, or column vectors is better said. And all of this is going to just boil down to this augmented matrix. Here's A, now augmented with U. And we care very deeply, where are the pivots going to be in this system? If the pivot is in the rightmost column, then the uniqueness consistency theorem says inconsistent. And inconsistent will say U is not in that span. So we're just looking at where the pivots are going to fall. First, we'll write equality and just write it in the matrix 2, 0, 1, 5, 1, 2, -1, -1, 0. Here's the augmented portion, 4, -1, 4. And let's begin our row reduction. Looking at that, that's kind of a nasty row reduction so far. One thing as a reminder about these problems is our author put a lot of care actually into rigging the numbers, so the arithmetic is not horrific. They're pretty nice, but that depends on the method you take. If you divide by 2 in this row, the algebra or arithmetic on this might kind of blow up and get nasty. It's a better idea to just switch out rows 1 and 3. Swap those out and no fractions in your problem. Look for ways to avoid fractions because there's always a path to do that. So let's make that swap. I'm going to write in row 3 to start, 1, 2, 0, 4. Row 2 doesn't change, so 0, 1, -1, -1. Row 1 is now row 3, 2, 5, -1, +4. So it's a good idea to look at the numbers really carefully, especially if you feel like you might have dropped a sign or something like that. So let's keep on going. At this stage, that's a better pivot position to have. We want to eliminate the 2 right here. So here's what row reduction will look like next. Copy in rows 1 and 2, 1, 2, 0, 4, 0, 1, -1, -1. Oh, I lost my red dot. There it is. Multiply by -2, add to row 3 to get -2 plus 2 for a 0, -4 plus 5 for a 1. No change due to the 0, so copy a -1. -8 plus 4 for a -4. So that's where the new matrix lands. We've got a pivot here. This one's all set up. This is a spanning question, so we just want echelon form. We don't care about reduced row echelon form. So in that next pivot position, we need to eliminate that -1 right there. So we have row equivalents. Let's start with that. We're copying in rows 1 and 2 again. 1, 2, 0, 4. 0, 1, -1, -1. And now the operation starts. Multiply row 1 by -1, add to row 3. We'll get 0, then next, -1 plus 1 for another 0 here. This will be +1 plus a -1 for a 0. And this will be +1 minus 4 for 3. Now, it's a good idea to bring in the fact that this was an augmented matrix. Analyze the pivots once more. The new pivot position is in row 3. Oh, thanks for spotting that. It's also a -3, importantly. And it lands right there. Thanks for spotting that negative. Well, we did it, folks. That's the end of the row reduction step. Now we just have to write out our conclusions to this. First, we should say something. Is this consistent or inconsistent? Absolutely. So for our showing our conclusions clearly, we need to say that inconsistent. There's a lot of questions on how much detail should you specify. You could say this is inconsistent because there is a pivot in the rightmost column. I'd say that's not a bad idea, but I'm going to try to write down the conclusions as what I would consider really the kind of minimum for full credit and almost the expectation on exam setting where you're not trying to write down every single little thing. So this theorem is just so massively common that you don't have to specify, say, there was a pivot in the rightmost column. I'll just assume that if you row reduce to this point, you know it's inconsistent by that theorem. You don't have to cite it or the portions of it specifically. So it's inconsistent because we have worked these problems and used that theorem. Here's the actual conclusion. So U is not in span A1, A2, A3. And that's our conclusion. So for a full credit on this kind of problem, we should show the row reduction. If you skip a step or two here, I'll just assume that you're getting fluent with it and you might have done a couple things in your head. But you have to say your conclusion to the row reduction, either consistent or inconsistent, so I know that you know, and then address the conclusion of the whole problem. It was about if U is in the span of the columns of A, so we had to say no for this case. Well, you did it, folks. That's working out these kinds of problems. Any questions at all with this one here? Okay, the thing that we just experienced with examples 4 and 5 does happen in the homework. In the homework, watch out for a question where they say, is B in the span of, excuse me, if every B is in the span of the columns of A, that's a totally different question than if a specific one is. And notice, if we try to use theorem 4, we would have found there is not a pivot in every row. Because if we use theorem 4, this is what the row reduction would have looked like. We would not have even augmented. And so we would have row reduced here. Theorem 4 is of no help. It doesn't tell us if U is in the span or not after all of that work. We would have to re-row reduce, bring in the augmented part, and see what happens here to fully address the question. If there was a pivot in every row, we might have got lucky, but for these kind of questions, it's probably better and best practice to just work it this way and see how it falls. Well, let's try now. More work with theorem 4. It's an important theorem, so we want to get some good practice in this section, and we'll be using it in the further sections. Like this theorem right here, we don't necessarily cite it every single time we use it. We just have to mention the specific parts that we're using as we go through. So that makes this question, example 6, kind of weird. And I wrote it out like this intentionally because it does sometimes look like that in your homework sets. Occasionally, vectors are written sideways and they're comma separated. Reasons why someone might do that is maybe they're saving space of your book, so they print less pages. That might be one reason. But our author changes the notation just so we're fluent with different ways of seeing these vectors. So we have 1, 2, 3 vectors. And the question is, does that set of vectors span R4? Why or why not? Well, let's see here. Does V1, V2, V3 span R4? That's kind of an awkward question, right? Because spanning has to deal with the columns of a matrix A, and no matrix was specified. That's okay. This is pretty common. What you do is you grab your vectors, just throw them into a matrix A. So let's say A is going to be V1, V2, V3. Expanding that out, it goes 1, 0, -1, 0. Next row, or excuse me, next column, not good to mix those up, comes from here, but we read them out in a vertical notation. 0, -1, 0, +1. Finally, 1, 0, 0, -1, going column-wise. All right, so we have a matrix. Next thing you might do is, let's state the size. Is this 3 by 4 or 4 by 3? Anyone see what size this ought to be? Good call. This one has 4 rows, 3 columns. So 4 by 3. Now, if you see this problem, you might row reduce it, but I propose a different alternative. The question is this, and that's going to be true if and only if A has a pivot position in every row. You have to ask yourself, is that possible? I agree. That doesn't look good. How about for someone in Zoom? Anyone see why there's no way to get a pivot in every row? Be kind of hard to see at first, but one thing I would try if you're not sure over Zoom is I would probably just start circling pivot positions. Now, I don't know exactly where the pivots would be in this matrix, but I'm going to imagine the best case scenario, maximum amount of pivots. I would find one here, here, and here. And this is best case. We're getting 3 at most. The reason we can't get another pivot is to get the next pivot from here, you go down 1 and you must go to the right for your very next pivot. They never overlap on the same column. They're always different in different columns. So if you saw this problem in the homework or say on exam 1, you can pretty much say this. There is at maximum 3 pivots. And so there cannot be a pivot position in every row. I'll say pivot in every row. So this is part of the work. Then we have to address this question. Does V1, V2, V3 span R4? Well, let's take a look. This was false, and so this is automatically false. We're referring to the matrix A when we say that conclusion. That's not too bad. We can just say this shows. Let's actually use a more special pen for a conclusion. It's easy to miss a conclusion, so we should try to make them pop. This shows span of V1, V2, V3, which is equal to the span of the columns of A, is not equal to R4. That's kind of wordy in a way, but that's one way you could write out. Or you could just say, for a more abbreviated version, span V1, V2, V3 is not equal to R4. If you wrote it this way, I'd say that's just as good as writing it out up here as well. It's good to see both ways, so we wrote it out this way as well. What happened to that A though? That seems like it moved. This shows V1 to V2, V3 equals the span of the columns of A. It's not equal to R4. I don't know how that moved, but it looks like it did. We'll leave it over there now. Well, any questions or comments at all, folks, on this one here?
Yeah, I have a quick question.
Yeah, go ahead.
So looking at A where you have V1, V2, and V3, so that is 3 by 1 matrix, right?
This right here, it's
Yeah, I mean
actually a
the
vector
vector.
matrix.
What is it?
So this matrix you're saying right over here, the V1, V2, V3, this
Yeah.
one's still thought of as that 4 by 3, only because the V1, for example, has 4 entries right here.
Oh, I see it now. Okay,
It looks funny for sure, right? But it's only because these are actual vectors rather than a real number. It takes on this size rather than a 1 by 3.
okay. So I was just getting the
From there.
scalar and the vector and matrix mixed up from I got it now. Thank you.
Gotcha. Thanks for asking that question. Lots of weird notational kind of things we have to kind of get absorbed and used to seeing in this course. Other questions or comments at the moment? Okay. Other thing to mention about linear algebra is it's kind of weird, especially after other math classes. We've hinted at this before, but it's probably good to remind ourselves. For me, the analogy is this. If you take a class like, say, calculus or that sort of thing, even differential equations, it feels like business as normal. Your conclusions is usually just a number. The integral of something is this value, or the derivative of something is this function, and that's it. But the moment you get into linear algebra, it feels like learning biology, where everything is stacked and determined by the definitions and the concepts and the rules behind them. That's how linear algebra works. And this picture right here is kind of an indication about it. All the questions come through these 4 different concepts, and the way we answer some of those things looks like this. We didn't necessarily even have to write that in, and we have the right conclusion. In linear algebra, our conclusions are sometimes not numbers, but sentences, descriptions, and that kind of stuff that's tying together the core concepts, whether they be definitions or theorems. So this is what sometimes the work looks like in linear algebra. There's not a lot of it, but this is one of those spots where we do encounter it, all because of theorem 4. Well, let's try out another one. Example 7 asks the question, or related one, does the vectors V1 and V2 span R3? Now, if you can imagine, if you copy the strategy, you could put this into a matrix, and there would be a pivot in every row. However, still, this is a suspicious question. Anyone see what's weird about it? 2 by 1? Exactly. If you're looking at the dimensions of these, as you said, this is of size 2 by 1. That's a dimensional mismatch immediately. It's not that the question was bad, although in a certain way it kind of is, but it's a question about, we have to look at every single portion of this and make sure things really match up. Even if it's a superscript describing R3, that's massively important because R3 is a set of all vectors containing 3 entries, not 2. So here we can say no, and that deserves an exclamation mark this time, because V1, V2 are in R2, not R3. Just as you said, definitely watch out for the size of things. Things have to match up very carefully. R3 itself, as a set, it would look like this. R3 is the set of all vectors that go x1, x2, x3. So we need 3 different entries altogether, such that x1, x2, x3 are any real number. In other words, they came from just ordinary R without a superscript. So R3 must have 3 different entries. If the question gives you things with 2 entries, It's an automatic no, nothing's gonna work here. Everything's essentially undefined in that sort of sense. Does that make sense with that question there? Awesome. Other questions at the moment? Okay, well, looks like we've got one last one. I felt like after doing something uncomfortable, like on example 7, we should do something that feels a little bit more positive, like this one, example 8. How about for folks in Zoom today? Would you say yes or no to this question? Would these span or not span? Any volunteers over Zoom? Quentin says yes. I agree. Thanks, Quentin. For this particular matrix, well, I said matrix, and that's already kind of a mistake. Sorry about that. It should be spanning R3. Yes, absolutely. Thanks for mentioning that, Prem. So we have to have R3 there specifically to make this statement work. If that was an R2, all bets are off. Even if there is a pivot in every row, the actual vector space itself would have been wrong. Still have to write out a conclusion, so we might say, since, actually, let's go this way. Let's pretend this is an exam problem, and we're just trying to run through it. We know the answer. We're just trying to put it on paper fast. I would go A1, A2, A3, A equals A1, A2, A3. I probably wouldn't do this step, but let's do it for the notes anyways. It's equal to 1, 0, 0, 2, 5, 0, 3, negative 8, 10. Here are the pivots. And we can say A has a pivot in every row. And that automatically implies, we use this word to say if this, then that, or we can read this as just implies. Actually, let's put that down on the notes. We'll see that quite a lot. This means implies. And if you see the bidirectional, that means you have equivalent statements, much like theorem 4. And this one is the if and only if as a shorthand. So A has a pivot in every row. Down here, this implies directly span. I don't even want to say the columns of A. Let's just use notation. Span of A1, A2, A3 equals R3. That means you can pick any vector in R3, anything that has 3 entries. You get to pick your favorite numbers, and we will find the right linear combination using the columns of A, or just the right vector to multiply it against to result in that particular choice of a vector. So that's what spanning means. But we did it, folks. That's working through our theorem 8, getting through these kinds of questions. Any questions or comments so far? Okay,
Yeah.
well, yeah, go
Listen,
ahead, sorry.
could you please explain spanning one more time? Like how you were explaining?
Absolutely. That's a tough concept, so I'm really glad you asked about that. So when we write out something like span right here, let's put a quick border. What we're really saying is span of A1. Let's give these some colors to make it show up a little bit better. In words, this is the set of all linear combinations, and that's absolutely true, and it's not a bad thing to remind ourselves. But saying it in words and actually writing it down are two different things. So when we say span A1, A2, A3, we really mean this. We're going to take an X1, or you could put C1. There's are really just notationally up to you. X1, A1 plus X2, A2 plus X3, A3. So it's a set of all vectors that look like this. This is what we refer to as the linear combination, such that X1, X2, X3 are in R, ordinary real numbers. So that's what the linear combination looks like. And when we say span A1, A2, A3 equals R3, here's what we're really saying. It means for an arbitrary, meaning random or any such vector, X equals X1, X2, X3, or hang on, let's use something that doesn't cause a notational conflict. We already used up x1, x2, x3. For an arbitrary v equals v1, v2, v3 in R3, we can find specific values of x1, x2, x3, such that spanning is kind of a lot of work sometimes. It takes a lot of writing to put all this into context. But this is where the x1, x2, x3s are coming from. We can say such that v, let's write it this way, equals x1a1 plus x2a2 plus x3a3. There's a 1 there and a3 there. So whatever choice you made here, maybe it's 1, 2, 3, maybe it's 0, 0, 0, or pi square root of 2, square root of 4, who knows, or square root of 4 is 2. Either choice you made, you'll be able to find the right combination of x1, x2, x3. So this linear combination equals that choice of v. All because we said span of a1, a2, a3 is R3. It didn't matter what you picked from R3. The span contains now everything. Does that make sense to folks with that question there?
Yes, it does. Thank you.
Yep, you bet. Thanks for asking about that question, Prem. That's always a technical question, so it's always worth taking another look at it each and every time. If you can draw it, if you can write it out, if you can say it in words, the more you kind of work with it, the more it comes together. And it's always an important question because of this. Without spanning, we have no idea what a basis is, and we cannot describe the dimension of a vector space. We lose more than half of linear algebra without spanning. Any other questions or comments at the moment? Okay, well, I think this is probably a good spot for the notes to settle down. We've addressed all the homework problems, and we're actually at the end of the notes. When we come back to class, essentially, this is what we're going to be looking at. When we come back to class on Thursday, we'll be dealing with, oh geez, where did it go? Sorry. We'll be dealing with these things right here, a matrix equation. The only difference is we want to find the solution sets now. So we're going to be going for reduced row echelon form, going beyond the echelon form. And the right-hand side is going to be zeros. We're going to look at homogeneous systems. We want the full solution set, and we'll describe it in something called parametric vector form. Yet another hugely pivotal section for linear algebra. Well, we'll settle today. We'll call this the end of the notes. If you have any questions, I'll be happy to help you out. But otherwise, see you all on Thursday where we'll be in 1.5.
Thank you.
Betcha. Thanks for the participation in Zoom, folks, and in class as well.